Welcome at the User Summit. We did a show of hands who was here last year, and I think like half of the people were there, so the other half probably has no idea about this topic. So my name is Han-Wen, for fun. I've been writing this search engine for source code. And so it's called Zoekt. So here we have the search engine. So you can clearly see that I'm not a big web UI person. But it is running in public on the site of my dear friends in the Bazel team. And it has a bunch of source codes indexed, about 31 gigabytes, mostly Google source code. So you can look inside the Android project for things that have the word telephone. And then you get lots of results. Git was created by Linus Torvalds, and he often has not exactly diplomatic use of language, but if you want to know where he does this, you can find that in 9 milliseconds. So it's really fast, and it's open source, and you can run it on your servers or on your laptops. But if you want to just check it out, you can go to this URL. And so why did I do this? So I work at Google, and most of my time I actually spend looking at other code and trying to understand what it's doing. And I frequently have to dig into code that I don't know and I don't necessarily have checked out locally. And so I use Google's internal code search for that. And so I missed that when I started to work on Gerrit, and I thought, well, I can solve that. I just built my own. And so last year, I announced this site running at this code search site running at the Bazel site, but it was kind of the first instance. And so I've been running it for a year and finding lots of bugs and ways in which it can break. And I made a number of improvements. And so I wanted to show some of those today. So what is there today? So I did an intro just now. I wanted to talk about quality improvements. So I'll talk about Unicode first. I'm not sure if I will have enough time to talk about the other one. I talk a little bit about security. And actually, we had a hackathon this weekend. And I also tried to address the most frequently asked question from the Gerrit community, which is, does it support Gerrit ACLs? And so hopefully, we can get some kind of answer to this intriguing question at the end. So when I started this, the core of a search engine for code is basically an engine that can find substrings in a large corpus of text. And so those substrings can be arbitrary substrings. So most search engines, they let you search for words. But if you take like the last character of the word, so you can look for crazy idiot, but then if you look for crazy idiot without the Y at the end, then it still works. And so most search engines that you have, like ElasticSearch or GitHub, don't do that. OK, and so it works. But I built the whole thing based on the idea that everything is bytes. Everything is ASCII. But in reality, a lot of text is not just ASCII. Maybe there's someone from Sweden, and they have like this little A with a circle on top, and then it's no longer ASCII, and then you can't search for their names. And so that's kind of a bummer. And I thought that, that's kind of works, but it doesn't really work. And more specifically, the regular expression engine uses Unicode. So the part that looks for strings uses one idea of what text looks like, and the regular expression engine uses another idea. And so that leads to bugs, things that are there, but you can find them. And it happens surprisingly often. So the source code of this search engine, for example, has Unicode because it has to test the Unicode support. And finally, it's just a bug. And so to me, this is, you can see here the Mount Everest. And so why do people climb Mount Everest? Well, they say, because it's there. And so why did I want to fix this bug? Because the bug was there. OK. Well, before you can understand what the bug is, you first have to understand what Unicode is and how the thing works before you can understand why it didn't work before. So let's go to how it works. So the idea of searching is that you build some kind of additional data structure called an index that will let you find things. And so here I have a very simplistic corpus. So we have two files. One contains the word code, and the other one contains the word model. And so what we do is we split it up in chunks of 3 characters. And we record the offsets of each of those groups of 3. So we call them trigrams. So you get this index, and you get these offsets. Now, if you want to look for a string, for example, the string temperature 50 C max, then you take the first group of 3 characters, which is TEM, and the last group, which is MAX, and then you look for these at exactly a distance of 10 characters apart. And because we have this additional data structure over here, we can do that very efficiently. So we have only TEM, so maybe somewhere in this table over there, there's TEM, and I only have to look at one row over here, maybe another one over there. And so it's very fast to find. If the string is not there, you can determine it very quickly. If the string is there, these offsets over here will give you the position where you then do a real string search. So that's very fast. In practice, you almost always want to look for things disregarding case. And you can also do that. So in this case, if you want to do it case insensitively, you generate all the different flavors of cases for the first and for the last trigram. And then you do the same strategy again. So what about Unicode? So Unicode, in essence, is a mapping of numbers to meanings. And so you, for example, the Unicode character number 25991 is the Chinese character 1, and so 1 is part of my name. So Unicode. So numbers mapped to meanings. And so Unicode, in essence, is a very big book, which has a list of these numbers mapped to a list of different characters. So the predecessor, obviously, is ASCII in 1963, which defines the common characters like ABC. Then in 1988, they made version 1, which had space for 65,000 characters. And the people that invented it were clearly, I assume that they weren't too familiar with Asian languages, because it turns out you can fit a lot of Chinese and Japanese into that, but if you want to really have all of the characters, then it's a little bit tight on space. And so then in 1996, they made a second version of Unicode, which has much more space, 21 bits of space, 2 million characters. This used to have an Egyptian character, but when I show it in this bigger size, the Egyptian character doesn't render anymore. But fortunately, here's the poo emoji. So with the new standard, you can do represent the not only, well, so Chinese is like pictures that evolved into characters. And so maybe the teenagers of nowadays, they use emoji to communicate. And so if that evolves into a language, we can also represent that future language using Unicode. So, but it's important to remember that it's not really, it's basically a book with numbers and characters. It doesn't say anything of how you store this data, and so there's an encoding needed for that. And there's different encodings, but the one that has basically one is UTF-8. And it uses a scheme where the ASCII characters have the upper bit 0 over here, and then you have 7 bits of data. And then if you have a character, a code point that needs more space, you use multiple bytes to represent them. So the pro is that ASCII stays ASCII, which is really nice, because in reality, most strings and file names, they're all ASCII. and so it's a space saving. Disadvantage, because each character can occupy a variable amount of space, if you want to have the thousandths, if you want to do indexing, you don't really know where the characters start anymore. And for most applications, it's not a big problem. Unfortunately, for code search, that is a problem. And now you could think, well, why bother? We could just pretend, use trigrams, and if we find a character that is very big like this, we just make a trigram that looks like this over here. And that kind of works, except that there's a catch. So the catch is that suppose you're not searching for temperature 50 Celsius max, but you're searching for 323 Kelvin max. Maybe you're a physicist and you like Kelvin temperatures better. Well, in that case, if you're using Unicode, you could be using the small k, the large K, or symbol 212A Unicode, which is the symbol for Kelvin degrees. And it turns out that the symbol for Kelvin degrees actually takes 3 bytes. And so if I'm looking for this string over here, I want to look for TEM and max, M-A-X. But what distance do I pick? Because if someone is using Kelvin in Unicode, then it's distance 12. But if they're using the uppercase K, it's distance 10. And so basically, this scheme doesn't work anymore. So I had to change the search engine to use Unicode for trigrams. So each character is 21 bits, so you have three of them is 63 bits. It fits nicely into int64, so it's nicely efficient. And I store all the offsets in terms of Unicode code points. So if we take the example earlier, we have code, and someone writes poodle but uses an emoji. Then you regard the emoji as one occupying one character position. And so you can still do the search. Then using this table over here, you can find where, in terms of Unicode code points, the string is. But then you want to do the actual comparison, you have to find the offset in the file, and then you have to compute bytes. And so we have an extra table that every once so often over here records where the mapping between Unicode code points and bytes is. So because this one is wider, you can see that code point number, offset number 6, is actually at byte 9. And so it works. So I put this on a machine that is hosted in the Bazel project. So it runs on the Google Cloud infrastructure, and since I work for Google, that's also nice because I can finally understand what customers go through when they try to use our product. Deploying is always good because when you use your software for real, then you find the real bugs and the real issues. Of course, Google is also a company that takes security seriously and also takes privacy seriously. And so this is a project that I do for fun. I go by train once a week to somewhere, and I have a couple of hours of kind of free hacking time. And so I use those train hours to work on this. And so it's for fun, and I don't want to have a lot of trouble with it. And one way to get into trouble is to do set cookies on your site, which is subject to various laws in various countries. And then lawyers come and talk to me, and I don't want that. The other one is security breaches. So if you do something that exposes the machine to bad people will do bad things with the machines. And then other people at Google come and make my life difficult, and I don't want that. Finally, also, so here you see this image. Does anyone recognize this image? Cultural reference. So it's an image from The Matrix Reloaded, where Trinity uses it uses an existing exploit for SSH to gain access to the power grid of the matrix. And so what my personal goal is also to not, for my search engine not to be in any movie where the bad guys try to get in. Okay, so this is part of my no headache policy is don't be implicated with bad guys in the movies. So if you talk about security, you always have to think about a threat model. What do I have that people want to steal from me? And so in case of a code search engine, you could be indexing private code, and so if someone managed to steal that, that would leak. That's bad. In my case, it's not a problem because I'm only indexing open source code, so it's all public. So I'm good. There's an SSL key, so we serve traffic securely, and so if someone steals that key, they can do a man-in-the-middle attack and show you source code that is subtly different from the real thing. How bad would that be? I don't know. In my case, it's not a problem because the load balancing is provided by the Google infrastructure, so you upload your private key into the load balancer, and then the only way to get it to do something with it is to basically hack your Google account, which is pretty well protected. So there's access tokens, so I need to get the source code onto the indexing machine to index it. In my case, it's a GitHub public token, so it's not a big deal if it gets lost, but maybe GitHub will get really upset with me if that gets misused somehow. Finally, if you can get access to the machine, you can do all of the above, and you can use the machine to do other attacks, to mine bitcoins, and to do other bad things. That, again, I don't want to do because then people come and talk with me, and they talk with my manager, and bad things happen for me. So how would you get into such a system? Well, the search engine itself is written in Go, and Go is a memory-safe language. You cannot, the worst thing that you could do to it is to make it crash, and then it gets restarted again. So no big deal. But there's one part of the search engine which is really important, which is the thing that provides symbols. So when you are looking for something, you usually want to have the definition of a symbol. And so I'm using a program called ctags for that. This is a program written in C that parses lots of languages. And because it parses languages, it can understand where the identifier definitions are. And so I store those identifier definitions so I can give back better search results. But it's written in C. And so if someone would have control over the source code that I'm indexing, they could create source code that looks really suspicious and maybe exploit some kind of error in this 100,000 lines of C. For example, the ANSI C standard says that identifiers can be at least 32 characters. And so I hope they didn't do it, but suppose they used a fixed size buffer for that, and then someone creates a commit that introduces this variable that then overflows the buffer, and then somehow it tries to dial a 4-pay number. So that would be bad. And so how do you deal with that? And so you can take inspiration from other projects that have the same problem. So for example, Chrome is one of the most secure web browsers out there because they use sandboxing. So the part that renders the HTML, which is essentially untrusted, is put inside a sandbox where it can do almost no damage. And so if you find a problem in the renderer that you can exploit, maybe you can exploit it, but then you're in a place where you cannot do any damage. And basically, I use the same technique for the indexer. So I run the untrusted binary inside a sandbox. I ship the content to the ctags binary, and the ctags binary responds with JSON containing the symbol definitions. And so this is technically how it works. So it's called seccomp. It only works on Linux. Don't ever run your critical infrastructure on Apple servers. So basically, you start the program, you declare what kind of system calls it can do. So in this case, it's really simple. You can allocate memory, you can read the input, and you can write the output. And then you can forget this, but when you exit the program, it's actually also a system call. And if you forget to declare this, when you try to exit the program, your program gets killed. And then you call seccomp, and then it's done. And so here you see how I'm peacefully sleeping, because now everything is secure and I don't have to worry about anything. I hope you've understood a little bit about how search engines work. I hope I managed to get across it. It's kind of an interesting and fun problem. I spent a year, some part of a year, well, the Tuesday afternoons in the train, on getting my search engine productionized. So I did a number of improvements, and finally it's really secure now. And I would love for you to try it out and tell me what you think. What about ACLs? So we had a hackathon yesterday, and I had been toying with this idea for a while. I thought, what the heck, I'm just gonna go and do it. So the idea is that the ACL model of Gerrit is really complicated. And so the only way to understand if someone is able to view a piece of source code is to just ask Gerrit, can this person see the source code? And so part of this solution is to put an ACL filtering thing in the middle. So if you contact the web server to search for something, normally you start in the web server, and then the web server looks at all the different indices to ask for search results. So for the Gerrit support, I put something in the middle that before it tries to do that, it contacts Gerrit to ask if the person logged in has support access to be able to execute the search. And if the person doesn't have access, you just don't return any results. So how do you know who the person is? Well, I added some HTML magic that in case you don't have a certain cookie, then it goes to Gerrit, where I added a little plugin that then redirects back to the web server. And so the plugin knows who you are on the Gerrit domain, and using a redirect can tell the web server your identity. Has everyone seen that I'm an administrator? It's over there in the top. And so if I go over here, then you can see in the corner over there that I am indeed an administrator. And so it goes really quickly because it all runs locally, but it actually does a redirect to Gerrit, then Gerrit sends a redirect back to here and sets a cookie. And so if I want to search for things, then I can find results in the secret repository. So if I now were to log out, then there's another redirect going on to make sure I'm also logged out of the search engine. And then if I try to log in to access the search engine, it says, oh, no, who are you? You have to authenticate. So then I can become another person. Now I'm Rebecca. And lo and behold, I'm Rebecca. And so if I now try to search for the treasure, hopefully it doesn't work. Treasure, yes. So no results, right? And so this is how ACL support could work. Regarding the overall idea of how to make this work, I think this part that goes from here to there was actually a little bit complicated to set up, but I think it's a decent idea. This plugin over here that does this redirect dance is kind of quite hacky. and in a real deployment, you'd have to integrate with whatever authentication system people have on site. And so I don't know how LDAP works. And so if anyone is interested in this and wants to have this, I'm there to make it work, but then I need some help to actually integrate with external ID providers. Questions?
How do you envision this working by knowing what projects and branches the user could use and doing that in a performant way in case they can't read most information on the server?
So the ACL filtering can cache. The idea, my idea is that the ACL filtering would cache this. And the moment you do a login, actually you could prefetch for all the repositories you have index data for whether the user has access to it or not.
So only on the repository level? Not.
Sorry?
Not on the branch level?
Oh, so this check access endpoint was actually, I added it because we had people misconfiguring their Gerrit servers leading to confidential data being leaked. And so I thought, well, people should really test this. And so I made this so people can actually write tests that verify that persons have no access. And it actually supports branches as well. I left it off the slide because...
So from a performance standpoint, my question was more related to, so suppose you have a large amount of stuff you can't see. Would you be taking into account what they can see before you actually do the query, or
No, so the filtering happens before the query goes to the index. So by doing it over here, you skip, if the person has no access, you skip the entire search for that piece of data they have no access for.
And so if they have access to a lot of things, perhaps millions of refs, then the filtering might be rather slow on the front end.
So this is basically what I implemented in 2 days. Real life tests are to be, I would love for people to try it out and tell me how well it performs. So let me know. Other questions?
Just a follow-up on that. So does that mean the index is done once and then the access is checked afterward? So you don't do indexing depending on the access?
No, so the indexing is usually done offline or on a cron job, okay, because it generates quite a lot of data, and so if you do it sort of online, it's the entire point of the index is to make the online search queries be very fast, and so you don't do the indexing when the person is looking for the document. Okay, thank you.